Applying structure-activity relationships on phenylethanolamine drugs. Part 1. Before you watch this video, make sure you have seen the previous video of SAR of phenylethanolamines Part 1 and Part 2. It will help you understand this video better and avoid confusion. You can find the link to the previous video here or in the description box below. Along this video, we will use some abbreviations. SAR, for structure-activity relationships. And PEA, for phenylethanolamines. COMT, for catechol-methyltransferase enzyme. And MAO, for monoamine oxidase enzyme. Which both are metabolizing enzymes for noradrenaline. In this video we will apply the previously illustrated structure-activity relationship of phenylethanolamines on the adrenergic drugs. We will learn how the chemical structure of these drugs affects their activity and selectivity for different adrenergic receptors and consequently, their therapeutic uses. We will also learn some tips on how to recognize the structure of these drugs by their names. First, let us encapsulate the key points of structure-activity relationships of phenylethanolamines. The size of our substituent on amine group is a selectivity clue for alpha and beta, and may be a selectivity clue for beta subtypes. Increasing our size shifts selectivity to beta. The number and position of hydroxyl groups on benzene rings greatly affects PEA activity, selectivity and metabolic stability. Generally, catechol derivatives which are 3,4-dihydroxy are non-selective and have poor oral activity, while resorcinol derivatives which are 3,5-dihydroxy and 3-hydroxymethyl-4-hydroxy derivatives are beta-2 selective and have good oral activity due to their COMT resistance. Absence of benzene hydroxyl group decreases direct action opportunities on receptors. 2-carbon bridge is optimum, while increasing the length to 3 or 4 provides an antagonist. Substitution on alpha carbon affords MAO resistance. Hydroxyl group on beta carbon generates 2 optical isomers. R is the active one. Let's start with the catecholamines. The simplest catecholamine is dopamine, which has only substituents on phenyl group, and no substitutions on the amine group or the carbon bridge. Dopamine is a neurotransmitter that acts on both dopaminergic and adrenergic receptors. Dopamine is more selective on its own receptors, that is called dopaminergic receptors D1 and D2. So, at low doses, dopamine stimulates dopaminergic receptors. However, regarding adrenergic receptors, which are our scope of our interest in this video, dopamine also stimulates alpha-1 and beta-1 adrenergic receptors but at high doses, causing vasoconstriction and increased cardiac output. So, dopamine is used to treat shock and heart failure. This non-selectivity between alpha-1 and beta-1 originates from being a catecholamine derivative, in addition to the absence of substituents on amine group. And this specific dual selectivity may be due to the absence of hydroxyl on beta-carbon, as it is a phenylethylamine. According to SAR, selectivity on beta-1 can be acquired by a large substituent on the amine group. So, Dobutamine, in which the amine group carries an isobutyl substituent ends with a phenol ring, is a beta-1 selective used in case of heart failure to increase cardiac output. Dobutamine name has a prefix, do because it is derived from dopamine, while but infix came from isobutyl substituent on amine, and because it is a catecholamine, so it was suffixed by amine. A note to remember. Phenylethylamines, such as dopamine and dobutamine, are suffixed by amine, while phenylethanolamines are amines as well as alcohols. So, we will find them generally are suffixed by len such as noradrenaline, or by nol, mol or ol such as salbutamol. Thank you for watching this video. I hope you enjoyed it. There's more to come. Stay tuned. See you in the next video.